Let's get going. So just first, I want to just sort of make a plug for the the student evaluation, the CAPE things. So I just wanted to ask if you guys have the time. I know it's a pretty busy time right now, but it's something that I use a lot. Me and the TAs will look at these things and try to again find ways to improve the course. Especially this being my first time here at UCSD, I'm sure there's lots of things to say. So definitely interested in how again you felt about the discussions now that you've had sort of the whole time to go through those. And just, this is the kind of thing that people look at as far as, us as instructors when thinking about what classes to teach and stuff. So it's just a really important thing. And I find that, the more voices you hear, the better. So just want to encourage you to do that. All right, so let's get going. So today is going to be, we're going to kind of wrap up a few things with this whole idea of electricity and magnetism. And it's kind of good because along the way, we'll be able to start to review, I think some of the stuff that people found to be the hardest, like Gauss's law and Ampere's law, sort of while we're doing this. So it's kind of, we can knock out two birds with one stone. So you'll hear this a lot of times, like people will call this course E&M, electricity and magnetism. And so we're really going to try to hit home why we say that. And so we've seen a lot of different things. We're going to go through and talk about them. But basically what we're going to talk about today is this group of things that we call Maxwell's equations. And so it's a little bit different. So Newton did his equations. He did them all himself, basically. But that's hard to do. And so Maxwell collected a bunch of equations that we've seen almost all of them already. And he adjusted a few, or adjusted one and sort of changed it around. And these are sort of the Newton's, or the electricity and magnetism version of Newton's laws. Okay, so these really fundamental laws. And so we want to just kind of go through and reflect on them a little bit and sort of look at their meaning. So the first one we learned is Gauss's law, right? And so this idea that the electric flux, which is defined by this integral here, is equal to the Q enclosed divided by epsilon naught. So we talked about that. That would have been the earliest one of these rules that we looked at. And so these are sometimes called the field laws because they basically tell you how our electric and magnetic field laws work, essentially. And so what this is telling us is that it's a charge at this point that can, or at least one way we can create a magnetic field is with we've got to be real careful. One way we can create an electric field is with a charge. And so we did some work on that. And so I thought we'd just have a few review questions. Again, this is the kind of thing that could be on the final. And so here's cross sections of a three-dimensional closed surface. So we sort of just take this surface and just sort of chopped a cross section. The top and bottom surfaces, which are flat, are in front of and behind the screen. The electric field everywhere parallel to the screen is shown. Which closed surface or surfaces have zero electric flux going through them? So what do you think? Okay, so let's go ahead and look at this one. So I agree with the majority. Surface A here. And so again, it can be really tricky drawing these pictures because you're inherently drawing two-dimensional pictures. But the idea is that these shapes go out forward, and the electric field is always parallel to the screen. So there's no electric field going this way or that way, and it stays the same. And so you can kind of get the sense here that if you just look at these shapes, you can imagine that here there's some positive charge, right? Because the electric field looks like it's coming out that way. With this one, you can imagine there being some kind of a negative charge, all right? But either way, the flux through these surfaces, in part B, it's positive. There's positive flux leaving. In C, it's coming in. And then in A, it's just sort of passing through, okay, which implies that there is no charge. And this is, kind of, if you will, the conceptual version, or one way to think about conceptually Gauss's law, in that, by looking at the electric field at some surface, you can get a feel for what's inside that surface as far as charge goes, or at least have some sort of an idea. So here's another one. So let's look at this one here. So a spherical Gaussian surface surrounds an electric dipole. So there's a positive and a negative. The net enclosed charge is 0, which is true about this situation. So the electric field is 0 everywhere on the Gaussian surface. The electric field is not 0 everywhere on the Gaussian surface. Or whether or not the field is 0 on the surface depends on where the dipole is inside the surface. So what do you guys think about this one here? Okay, so let's call time here on this one. Looks like we got some really good conversations. Who wants to tell us what they were thinking on this one? Anybody want to be brave? Heard some really good conversations. That's good. Yeah, what about here?
So I said that I think it's not 0 everywhere because the dipole get partial negative signs on the surface.
Okay. Anybody else have a different take or have a different sort of viewpoint that they had? So I think I agree with that, part B. And I think the majority, again, sort of in that neighborhood. If we look at the actual picture here of, a dipole, this would be roughly the electric field lines of a dipole. And so you can imagine if you're making some spherical thing here, okay, like on this side over here, okay, sorry, it's more like an egg shape, but on one side you've got more lines coming in, on the other side we've got lines coming out, all right, and so the electric field at the surface in general here will not be 0, and so what Gauss's law says, though, is that the total flux, so what you can say is that if you add up all the flux, the positive and the negative, and so that idea of the electric field over that surface, and you do your surface integral, that will come out to be 0. All right, and so that's a really tricky one. So we actually had that exact same clicker question earlier in the semester, and we did, we were much more confused about it. Any questions on that there? Okay. And so here, this was one we had on a test. This might be a good one to kind of go over to review. And so a point charge is placed at the center of a spherical Gaussian surface. The electric flux, which my font changed it to F of E, so sorry about that, is changed if what? How is there a way we can change that electric flux? Okay, so I think that's probably about it, and I think we did really good on this one, so that's good. So if you look at so really high on that one there, so that's good. So we have that idea down. Okay, so on to our next Maxwell's equation. So this one here is what we call Gauss's law for magnetism, and it's just real similar to Gauss's law. So we still have, we talk about this thing, the magnetic flux, all right, and it's B dot dA, just like this here, okay? And so magnetic field lines, now the thing about it, we talked about this a little bit, but we haven't brought it up in a while, but the magnetic field lines are always continuous curves, okay? If we contrast that with the electric field lines can stop and end, all right? And so because these are always curvy, okay, if you make some surface, like a Gaussian surface here, what will happen is there's always the same number of lines going out as there's going to be coming in, okay? So there will always be no net magnetic flux through the closed surface. So this equation is a little more boring than the Gauss's law, because so Gauss's law, this equaled to Q, all right? So basically, but now it equals to 0. And what that really is the Gauss's law for magnetic fields basically is saying that there can be no net magnetic flux to the surface because there's no magnetic charge. And if you remember, we showed pictures like this of someone trying to be smart and trying to get like a magnetic charge, and so they take a magnet and split it up, and what you do is you just get 3 smaller magnets. Okay, so at this point in physics, there's no magnetic charges, which again, the idea there would be sort of like just the north side of a magnet hanging out there, right? Okay, we don't have that. We always get these 2 things together, all right? And so this is essentially a way to kind of say that mathematically. Okay, so that's 2 laws. And we got Gauss's law for magnetism. Now the next one is this idea of induced electric fields, which we've been talking about. And so in this figure here, we've got some magnetic field, and it's increasing. And what you do is you induce an electric field. Okay, and so something has to act to do that. And what happens to get that induced current? So when we talked about this in class, we talked about it very much in the sense of there's going to be an induced current. Okay, something's inducing a current. But what happens is, in some viewpoints, the thing that's inducing that current has to be an electric field. And we sort of talked about this, but we weren't super. And so this is the induced electric field, and this is Faraday's law. And so a way to think about this is these induced electric fields are going to be curly electric fields, right? Because we're always making, these currents we were talking about were curly in a sense, okay? And so we're going to use this same line integral that we used for Ampere's law here to represent this induced electric field for when it happens. And so this is just a way to represent Faraday's law just a little bit differently. And so this is a little bit closer into, there we go. So we were going to do a clicker question there, but now we won't. But this is just some stuff from last week, so it's probably a little bit fresher. But the magnetic field in this picture is decreasing. And so if you look at that top picture, okay, so the magnetic field lines are coming out. If it's decreasing, then you want to create a current that induces a magnetic field coming out, because you want to sort of keep nature the same, right? So the way that we would have talked about this in class for this stuff here would have been like this. So you had like a before and an after. And so here maybe there's like 4 lines coming out, and afterwards there's 3 lines. And so you want to make up that last line, which would lead to an induced current that way, which to make that induced current, you would be making, okay, an electric field going in this way here. So you'd be inducing an electric field, all right? A circular electric field, which would be, again, this is Faraday's law. So sort of cleaning up Faraday's law, then, we can write it sort of in a sense here. So it's really just the stuff we've been talking about, just a little bit more well-defined. And I wanted to talk about something interesting here that's a little bit getting out of the context of our course, but I think it's useful. And so let's look at this picture here. So this is the kind of question we would have answered last week. So here we've got a loop that's moving to the right, and there's some external magnetic field into the page. And so the question I want for you is there an induced current here? And if there is, which way is it going to go? Okay. And I think I agree with the majority here. All right, so again, the way that I would think about this is I would draw a picture and sort of thinking about the magnetic flux. So as this loop is leaving, so maybe in the picture there's like 4 magnetic field lines. So maybe a second later, there'll be 2 magnetic field lines. So again, like usual, we want to make our after. The goal that nature wants is sort of to keep the before. And so you'd want to make some lines going in, which would lead to a nice clockwise current. All right, so you did pretty well on that one. And so that, again, what we can think about there, again, so we're inducing this clockwise current. So now let's look at this here. So we've looked at pictures like this. And so here's sort of a case. This is similar, just sort of the loop's coming in the other side. Okay, but this loop is coming in. And so we talk about this. When the loop is moving, we said, okay, well, you got the velocity this way. You've got your magnetic field in. And so there's a magnetic force pushing up on this particle. And that's how we sort of talked about it. And we sort of refer to that as this thing called motional EMF. So by moving, okay, this thing, we're creating this magnetic force on the charges that makes our current, okay? Now, when you're thinking about Lenz's law, you're usually just thinking about, am I inducing a clockwise current or inducing a counterclockwise current? But if you actually look at the picture, like in this case, it's a magnetic force that's doing it. So now, okay, in physics, you probably haven't done too much about this, but sometimes it's useful to look at another reference frame, okay? And suppose you were floating around with that loop, okay? So that loop is moving, and suppose you were like walking with that loop, okay? So now in your frame, the particles in that loop are not going to feel a magnetic force because they're not moving relative to you. All right? You know, they're at rest relative to you. So when you watch this, okay, what happens is your interpretation will be that there's an induced electric field, okay, and that electric field is what causes this current to go. And so it's kind of a interesting situation because depending on which reference frame you are, now the results are the same. You get the same induced current either way, but depending on how you look at it, its cause is different. In one case, it's a force caused by, it's a magnetic force, and in one case, it's an electric force, okay? And so this is something that if you have a class on special relativity, it sort of depends on what your major is, but sort of special relativity is where you sort of connect these things here. But you'll see that that the idea of thinking about electric and magnetic separately, you can't really do that in reality. And so what happens is we talk about the electromagnetic field, which is where this idea of E&M comes from. And what's weird is like in situations like this, and those situations too, okay, what will happen is everybody will agree on the results. Like we agree that there'll be a current and we can figure out the current, and we've done this in class. but we'll disagree as to whether it's caused by an electric field or a magnetic field, or even sometimes it can be caused by both of them, depending on your viewpoint. And so what it is this idea of the electric field is you can't really separate them. They go together, and they really are just sort of two sides of the same thing. Okay, and so you get, again, we're just sort of bringing this up now. You'll get more into this if you ever talk about special relativity, but it's kind of a good thing to know. And so that's, and you can already kind of see that these things are related because, what causes a magnetic field? Well, a current causes a magnetic field, at least for so far what we know about. But we've also learned that a changing electric field or changing magnetic field can create an electric field. So these things, definitely there seems to be some deeper relationship there. But this is like another example where you can hopefully kind of see that. All right, so we've talked about the two Gauss's laws and then Faraday's law. And so the last one is Ampere's law. And I think that's the one, that's the hardest just because we sort of dealt with that just a few weeks ago. And so let's look at that again. So Ampere's law, states that whenever current passes through an area bounded by a closed curve, the line integral of the magnetic field around the curve is this here. And so we use this, and in a similar way to Gauss's law, we could use this to calculate magnetic fields for cases where there was a lot of symmetry. And the other thing that this sort of tells us is what causes a magnetic field. Well, we learned from that Gauss's law for magnetism, it's not magnetic charge. And so here what it's telling us is what causes these is a current. Okay, so sort of the basic fundamental piece is that currents create magnetic fields. And so let's look here. So this is what we had for our last quiz. So let's go back to this one here. So consider the two cases shown below. We got two pictures. So in case one, you've got this setup here where you've got sort of a cylindrical shell with current going into the page. It's hollow inside. And here you've got a cylinder wire. Okay, again, you can imagine these both coming out of the page and going on forever. And what we wanted to do is we wanted to compare the magnetic field at the point A in the two cases. So what do you guys think about this? And then we'll go in depth and talk about it a little bit more. Okay, so who wants to be brave and say what they were thinking? So I think the majority agrees with me there. So who wants to say what they were thinking here? Anybody? There's lots of ways to think about it, or kind of several ways to verbalize this, I think. Yeah, up here.
In case 2 is literally in the magnetic field. So it's feeling its full effects, while in case number 1, it's not feeling the full effects because it's a bit far.
Okay. Anybody else have other thoughts on this one here? I thought this was probably the hardest one on the test. I don't know. You could disagree. Yeah, what do you think? Yes, okay, so again, this is a tricky one. So if you look at A, right, and so to sort of expand on that here, we can actually look at this here. And so in case 1, so let's do this, case 1, if I was drawing the loop of interest, I would draw my loop right about in here, okay, and say, call that radius r or something, okay? And so then, so we'd have b dot ds equals u naught I, in that case there. And so here, you'd have b times 2 pi r, and like we were saying, the enclosed current for that Amperian loop is 0. Okay, and so because we have this cylindrical symmetry there, okay, then we know what that means is that, we'd have to have this sort of, this would have to be our b dot ds either way, and since I is 0, what that tells us is the B field for this case 1, so B field for case 1 would end up being 0. All right, and then again, sort of doing the same thing over here, you get sort of a similar setup. So again, we got this b dot ds deal, u naught times I. You get the same thing over here. So we're going to have b naught 2 pi r. And now here, this is one of those deals where you got to do like a ratio. And so we had, I think we looked at this one, exactly this one, in our discussion for that week. And so you'd look here at basically the ratio of the area. So your total current I is going through this thing here. And so you'd look at your ratio of areas. And so if I was to say, call this radius r, then what would happen here is that'd be pi r squared divided by pi r naught squared. And so that gives you a ratio. And so it gives you some kind of like a percentage times that current, tells you how much is enclosed in your particular loop. And so then for your last step, you'd say the b at point 2. Now you didn't need to do this, of course, on the test, but just to kind of go through and be real clear about this. And then you'd have r squared over r naught squared. And so it's always nice to go through and cancel out stuff. So you'd have r on top and r0 squared there. Okay, so when thinking about the magnitudes, this is going to be some magnetic field, where in that first case, the magnetic field would have been 0. And so this one will be bigger than that. Again, it's kind of good just to kind of go back and reflect on this. Questions here? Like I said, I think this is the one that's, I think at least, is the trickiest. Gauss's law is definitely not easy, or Faraday's law, but I think this is the one. Okay. And we'll have, again, more time to kind of talk about these things in review sessions and such as we go on. But now, so at this point, if you go back in history, these laws had been created and people were using them, but you're going to find out that Ampere's law is incomplete. And so to do it, it's kind of a subtle picture. And so let's look at this here to kind of convince ourselves of this. And so, we sort of talked a lot about, okay, so with Ampere's law, we make some loop, and then we, think about, imagine there was some sort of film there, all right? And the way the Ampere's law works is we can relate the B field around the surface of that loop to how much current is going through that soap film, okay? Well, now sort of imagine that this is like some sort of like rubber or something, okay? So we're trying to kind of work with this a little bit, okay? The thing is that we've dealt with these flat here, but there's no reason that we can't sort of play with that a little bit. So imagine taking, this sort of rubber surface and kind of stretching it out like so, okay? And so now you can think about kind of two surfaces, this surface here, but also this surface here that's sort of pulled out, okay? And so it's the same sort of picture when we do Ampere's law here. We can relate the B field that's going around this part, okay, to the current. And the thing is, we can use either one of these. We can either sort of use our just traditional flat piece where the surface is right here, or we can use this piece where if we sort of pull like on that soap film, okay, the actual parts that would be being pierced by The current would be over here, and actually this piece here, there would be none of that soap film because we sort of pulled it away over to here. All right. Now, in the case of just what we've dealt with primarily, which would be just say one long wire or something, right? It doesn't really matter because the current here is going to go through this surface and eventually pierce through this surface. And so either way we do it, we're going to end up with the same result. And so we didn't really talk about that much that we could have that option just because it was just easier to go like this here. Okay, but just stop for a second and make sure everyone kind of visualizes this picture. Does everyone kind of see what I'm meaning here? So we want, when we're doing this Ampere's law, we're relating the current going through sort of that soap film around that Amperian loop, but we can play with that soap film and basically make it any kind of shape we want to. But it's just like an imaginary shape that we're making up. And now, where this becomes important is, and like I said, in most cases it's sort of not really that big of a deal, but here's a case where it becomes important, and this is what Maxwell, his big contribution to this. Okay, so again, he's sort of the Newton for electricity and magnetism, if you will. He's the one that sort of combined all these and kind of completed the picture, if you will. And so if you look back at the days where we were charging up capacitors, okay, and so this picture here is sort of like looking down, and so here we have our Amperian loop, and so you can kind of imagine, so this would be sort of our surface right here as I was describing. And so we have two surfaces. We have sort of the traditional one here that we've always dealt with, and then we have this one where you pull the soap film back, okay, like so. And so this is 2 plates of a capacitor. And so what happens is in this picture here, we set this up, and it might be good to draw maybe sort of a bigger 3-dimensional picture over here. So instead of our traditional wires, okay, I'll draw this ending in a capacitor plate. So I'm sort of charging up my capacitor plate, all right? And so we can set up this second surface. So the second surface doesn't actually have current going through it, okay? Now this first surface here does, the current's coming in here, so there's current, building up and charging up this capacitor at this moment. So we're sort of charging the capacitor, but there is no actual current passing through this second surface. And so this is something where that's, we sort of, if we take the same equation and look at it in different ways, we get different answers. And so in one case, it's telling us the current through it is 0. In one case, it's telling us the current through it is I. And so that's not good. And so what Maxwell did is he added a correction to this. Okay? And so now in the Ampere's law, there's 2 things that can contribute to that magnetic field. There would be a current, and there's also this extra term that works out to be proportional to a changing electric flux. So right here. Okay, and he called this the displacement current. And so it's like an extra piece here. Okay, so basically when there's a changing magnetic field in that region that you're talking about, it can induce a magnetic field. And so that was his big correction. So if you look at then this law that some people will then call the Ampère-Maxwell law, since he changed it, so it states that a changing electric flux through a closed loop or an electric current through the loop creates a magnetic field around the loop. And so that's where we get this here. And so this, again, is Ampere's law with the correction through it. And so when you actually see it written somewhere, okay, it'll look something kind of like this here. And so if we just kind of go back again, so what we're saying is that, all right, with electric field can be caused by a charge or changing magnetic field. And now what we're saying is that a magnetic field can be created by electric current or by a changing electric field. And hopefully, if you think about it, that's kind of nice to have that symmetry there. Okay, so again, like we're talking about how this is another instance where you can kind of reinforce this idea that electric fields and magnetic fields are interrelated. Okay, and so basically by changing one, you create the other, and vice versa. And so just to do an example of this, so let's look here. So this is similar to what we did with Faraday's law. So here I have this picture of an electric field over here. All right, and we say that this electric field is decreasing. Which of the induced magnetic fields would be created in this picture here? Okay, so this is a tough one. So we got the two big answers are this and this. And so I'm going to say that it's this one here. So a couple of things. So first, if we look back here, okay, so this is what we're saying here is so two things. So this is this new piece, okay, that sort of says that the changing electric field leads to a magnetic field, okay? And so that's the first thing is that's the relationship there. The second thing is this thing here, this is B dot ds, and so this is your magnetic field around some loop. And so if you look at the actual example we were talking about, okay, like in this example here, I've got current kind of scooting down this wire, all right? So that current is going to be creating some magnetic field that's like out of the page here and into the page here, right? And so the thing is, we want the changing, because if you think about it, over here on my capacitor, if I was to draw my picture, there's an electric field that's pointing this way. And as the current is building up, this electric field is changing. You want this electric field to make the same sort of magnetic field, right? Because just because I sort of pulled this shape into here, it doesn't mean the magnetic field changes. It should be the same magnetic field that's due here to the wire. So in general, this will create a curly magnetic field. And then the tricky thing is, if you look at this equation, we're used to Faraday's law, where there's a negative sign here, right? So the change in flux for Faraday's law is opposite what the induced EMF here is. But for this case, it's not. And so what you kind of do is you kind of look at this and do sort of the opposite is what you do for Faraday's law. So you say, my electric field is out. Okay, it's decreasing, which means the change in electric field would be into the page. And so that's the magnetic field that I want. So the magnetic field I'm going to get is going to be in the direction of the change, which would then be going around in that counterclockwise direction. So that's a really tricky idea. Questions on that, anybody? But now we have, and again, you can kind of think about it. So here's just our picture. So some of the examples that we might have used. So here there's a changing magnetic field induces a curly electric field, and a changing electric field can induce a curly magnetic field. So that's kind of what these equations are telling us. And so now we can write all these equations together. These would be Maxwell's equations. Sometimes you'll see people in physics departments make a T-shirt with these on them. They're sort of our big famous equations. And so this leads us, so this, we got a few more minutes. I'd like to get through this. So basically, what's kind of nice about physics is there's really only 11 equations, okay? Now, you got to do a lot of thinking to kind of be able to solve everything, but there's Newton's 3 laws, Newton's gravity, these new laws for Maxwell, and then this is our force law. This is the force on a particle due to electric field, due to the magnetic field, and then you guys will learn these if you go on to 2C, the first law of thermodynamics. So that's kind of nice. And then just the last thing is this idea. So this is kind of leading into 2C. Okay, so the other thing that Maxwell found out, which was really big, was that he found out that light, okay, is an electromagnetic wave. Okay, so with these equations, he was able to go through and predict that if you like vibrate a charge, it creates a wave, and if you actually, the speed of the wave he got was this. So these are these constants we use. If you actually go through and calculate this, this is the speed of light, okay? And so it was quite a revelation to realize that light and electricity, magnetism were interrelated. Okay, I'll be down here if you got questions.